Well, let's look at a more complicated, at least this, well, I think any way you look at it, whether we solve it ourselves by hand or try to get help with technology. If we look at, say, dx dt equals 3t times 1 minus x squared, this is still separable. I can divide both sides by 1 minus x squared and separate my variables. Now here are the initial conditions. But I can separate those variables into a left-hand side, which is dx over 1 minus x squared. I can get the right-hand side as 3t dt, and then I can do as before, integrate both sides, and I have my x-ent and my t-ent, where in the t-ent I add the arbitrary constant. I integrate both sides, and I'll show those. Now here I pretty much just have the code I had before, and I changed the necessary pieces. So I changed the differential equation, I changed the initial conditions, changed them here in the comments, changed them in the integration, and then down here changed the initial conditions. And if you just put that in, actually you get slightly better results than I thought you might, but definitely worse than we would hope for. So if I hit evaluate and on that old stuff and come down here and look at it, you see the left-hand side integrates to this. That was due to partial fractions, and you got that integral. Right-hand side was pretty straightforward. 3t becomes 3t squared over 2 plus our arbitrary constant. Then remember, the next thing I did was I tried to set this thing up here equal to this and solve for x. Well, it sort of does it, but notice I still have the log x plus 1 on this side. Not a big deal. I could exponentiate both sides, except I've got the log x minus 1 on this side. So it never combined those logarithms. However, notice it was still happy when I substituted in x equals 2 and t equals 0 into the equation up top here, this one, and solve for c. This is just substituting in. I did this this was an extra step. I didn't need this to show you all. I guess I just left it there. But I was looking at substituting in the x and the t. You should get this from the original code. It says c, and we can see that here. C equals 1/2 log 3. Then if I substitute that value of c into the original equation, I get this. And this looks, again, it sort of looks great, except I've got this log x plus 1 here and the log x minus 1 there. Okay, so it didn't, I have an implicit solution, but I don't have an explicit solution. But actually I know I can get one. So kind of what went wrong? I'm going to get rid of this substitute thing there. So I had to show that substitution. I'm just going to get rid of that. So that was our original. Now I've got a bunch of stuff down here all commented out that so I thought, well, maybe I could do something with this integrate, collect things or that sort of thing. So the first thing I tried was this collect common stuff. Now we'll have to, I'm going to go up here and put it here, uncomment that and comment this one. And now I went on Google and I typed in Sage Math, and I typed in stuff like collect, and got to get down to the bottom of this slide over, and it's this collect common factors, And so I tried that. And I hit evaluate, and it didn't work. I have that same thing here again. So I get all the other same results. So that didn't work. And then I thought, okay, so that one doesn't work. So I'll comment that out. And I looked around and I found this thing. Okay, I'm going to get rid of that because I just used it. Now I'll get this one. And I found this thing, simplify full, that I could put at the end. So I just took that original integrate and I stuck it in parentheses and then dot simplify full. And I thought, oh, that looks good, because I even found it on a help page where it was talking about Sage wasn't combining logarithms, and they did this for an example, and they were able to do it. And so I tried it, and it did not work again. So you see, it just doesn't seem to want to combine those. And I even messed around with it, tried really simple examples, and it just wouldn't do it. Sage just doesn't seem to want to combine those logarithms. So basically I went back to square one and said, well, I'll use the simplest command because none of the others work, so I shouldn't muck it up with this extra stuff. So I just have that simple command. But I thought, well, I can get rid of those 2's, or actually 1/2's. So after I did this, but before I try solving, I went in here and I said, well, let's update our integrals and multiply them by 2. So I take 2 times the integral, x integral, and assign it to the x integral. 2 times the t integral, assign it to the t integral, show those, and at least I have something that looks slightly better when I start here. So here's the old ones up here and here. Now here are the new ones, and I've gotten rid of at least that half and also a half here because I multiplied both sides by 2 is what I did. So multiplying both sides by 2, I ended up with this, which looks a little better, but we still end up at the same place. I mean, we still have these logarithms that are not together. And so the way I ended up having to fix that was once I simplified it to this piece for the x integral, I just did the rule for logarithms. I said the logarithm of x plus 1 minus the logarithm of x minus 1 is just the logarithm of x plus 1 divided by x minus 1. So I took that and I ended up just redefining my x integral as this. Now I guess I could show it again. I'm not going to, well, sure, let's show it again. We'll show both again just so we keep seeing them. So I'll highlight that, put that in there. So now I show both of those, and and I get that logarithm, and then I just do that same stuff again, and let's see how that does. Evaluate, and there's the original. There I had multiplied both sides by 2. Now I've combined that logarithm. Okay, so this I rewrote as this, but I had to do it. Sage just wouldn't do it for me. But once I did that, it could indeed solve for x. And you see, we get this. Now the interesting part here is that ended up causing me another problem, which I didn't foresee actually. Notice it gives me 2 possible answers for C. right? It says c equals log of negative square root of 3 and c equals 1/2 log of 3. Well, this one, the second one, is the one that we found before. And actually, we could, find c before we solved for x. I mean, we could do that. Obviously, it did it before. But, okay, this just shows, what do you do if you get something like this? Well, look at log of negative square root of 3. Well, that's undefined. Now, it's not undefined in the sense of complex numbers. That actually has an answer in complex numbers, just like the square root of negative 1 has an answer in complex numbers. So that's why Sage thinks this is perfectly fine, because it says, hey, it's just a complex number. No, we don't want it. We just want this real answer. But notice, when it gave us our final solution in that substitution part, it used this first one. Well, why was that? Well, come back up here, and the reason it did that, I'm not sure. Oh, I had some things in different order, so I just don't need that. See here, it's saying use C equal the first item in this list. Okay, the 0th item. We need then the next item, the second item, which is item number 1, because again, they start at item number 0. So if I just change that to a 1 and evaluate, I finally get my answer. And there it is. And notice that if I plug in t equals 0, I get 0 here, so I'll get e log 3, but e log 3 is just 3. So that's 3 plus 1 over 3 minus 1. That's 4 over 2, which is 2. X equals 2. Our C did in fact work. And so there is a more cumbersome and complicated case using Sage. So it still helped me. I mean, I didn't have to deal with some aspects of the, I still didn't have to deal with the integration. It did that for me just fine. That was great. So I got the integration. However, in solving the equation, I had to help it a little bit. I had to tell it that this is equal to that. Okay, and it just wasn't going to do it, without me telling it those were equal. And so, that's what I did. So as we look here again, this is the same code we did before. We initialize x, t, and c. Here I'm discussing what I solved. Here I'm saying integrate that left-hand side with the x's, integrate the right-hand side with the t's. And again, I don't need these things anymore because they didn't work. And then I showed what I got so I could see, and then I realized, okay, well, I'll multiply both sides by 2, and again, so xnt was the left side, tnt was the right side. I'm multiplying them both by 2. I looked at them again, and now they looked better, and it made it much easier for me to think about the fact that that left-hand side could be written, the difference of logs is the log of the ratio. So a minus b, log of a minus log of b becomes log of a over b. And so we really do have to know some algebra. Okay, we cannot depend on an algebra system doing it all for us. It just won't always. And they're not as smart as we are. They're really good at redundant calculation. We're not as good at that. We tend to make mistakes and so forth. But we are actually better than the system in many ways. Now, you give it some other complicated things, we could do those things, but it would just take us so long. But here, I do that one step for it, and so I changed that left-hand integral into this new form. But then I go ahead and do the same thing. I take the left-hand side, the left integral, equals the right integral. Solve that for x. It did it just fine, much quicker than I would have. And then I substituted in my x equals 2, t equals 0 to find c. Again, I could have done it before I solved for x. That would have been fine. But I kept it in the same order we had done with the first problem. And then I get that final solution by substituting in my correct value of c. So that time I had to update which position it was in. It wasn't in the 0th position, it was in the 1th position. Okay, and so we see that here. I didn't want this first c, I wanted this c. And again, I could, even if I hadn't done the original work, I would know that because this is undefined. And again, it's undefined in real numbers. We have to know that. But that's, algebra stuff. We were supposed to know this in high school. If you are rusty on it, it's just showing you should do your own work on catching up on things you're rusty on. I have to do it all the time. Okay? I forget stuff all the time. And so I have to go back and relearn it and look up rules and things like that. But Google is fantastic for that. Okay? So here we've solved a slightly tougher separation of variables problem. Okay, so we'll call that good.